My name is Wayne Fagan, and I'm chair of the D. Howard International Education Foundation, which is a nonprofit that does national programming, and we're based in San Antonio, Texas. And we launched a few months ago something that we call the Rural STEM Initiative with our partners at the University of Texas, San Antonio, Cleese College of Engineering and Integrated Design, for short. I'll refer to it as UTSA. And we are with the students at John Fredson School in Alaska, north of the Arctic Circle. The access to the school and to the community is by bush plane or dog sled, and weather permitting. Lots of technical challenges, and they are wonderful students, and they have wonderful teachers and a principal. And this will be our first virtual presentation. We will have 9 this year, and this is the first one, and we're just thrilled to be with you all. And with that, I'd like to introduce my colleague representing UTSA College of Engineering and Integrated Design, Jill Ford, for some opening comments from her as well.
Thank you so much, Wayne. And hello to all the students. We're so excited to be here with you. And hello to Principal Minot. We're just so happy to be. Well, my name is Jill Ford. I'm the Assistant Dean for Student Success here at the University of Texas, San Antonio, Cleese College of Engineering and Integrated Design. And we're so, yes, hello to all of you. We're so excited to be partnering with Wayne and with the D. Howard International Education Foundation, and to be able to be part of this wonderful initiative to connect with you and bring STEM-focused resources to our rural schools. So happy to be part of this and excited for this presentation, excited to have our wonderful faculty member, Dr. Combs, with us as well. And I think with that, I'll turn it over to Tracy.
No, let me just make a few housekeeping matters. So this presentation is being recorded, and then it will be edited and made available by UTSA on their social media and on our social media, D. Howard International. We'll let you know when that is. If you would, if you're not speaking to us, and if we're not a speaker, for audio purposes, if you will mute your mic when you're not speaking, and that will help the audio recording. And with that, I will turn the program over to my colleague, Tracy Thomas. Tracy is a middle school science teacher here in San Antonio, who I've worked with and admired for many, many years. She does fantastic programming. She is also chair of the Teacher Advisory Council for D. Howard International Education Foundation. And with that, I'll turn the program over to Tracy, and thank you all. And I look forward to seeing you on the video.
Thanks, Mr. Fagan. Hi, kiddos. Yay, awesome. Well, yes, thanks, Mr. Fagan. And I teach engineering. And as you can see behind me, I've got a rocket there, and my 8th graders build and fly rockets. So we have a lot of fun, and we're so excited today to have Dr. Combs with us. I have the pleasure of introducing Dr. Combs. He is an assistant professor at the Mechanical Engineering Department at UTSA and a D. Endowed Faculty Fellow in Aerodynamics. Before joining the faculty at UTSA, Dr. Combs was a research assistant professor at the University of Tennessee Space Institute. He holds a BS in Aerospace Engineering from the University of, he holds a BS in Mechanical Engineering from the University of Evansville in Evansville, Indiana. and a PhD in aerospace engineering from UT Austin. Dr. Combs is an expert in laser diagnostics and non-intrusive measurement techniques, specializing in the application of these tools to solve problems related to high-speed aerodynamics. This research with fluid dynamics and turbulence and combustions and lasers and optics and high-speed imaging and advanced data analysis and image processing can all be seen. He is the new director of a new lab of hypersonics research at UTSA. And he's an active member of AIAA and has worked on sponsored research funded by various organizations like NASA and private industry. So Dr. Combs, we're gonna let you take over, sir.
All right, great. Thanks for the intro. Good morning, everybody from Alaska. How y'all doing? It's good to see ya. All right, I'm gonna put up, okay, I have some slides if the host can enable screen sharing, whoever the host is, and I'll put my slides up. Okay, here we go. So you all should be able to see this, all right? So as it was explained to me, and as we just talked about, you all sometimes have to take a plane to get to school, right? Am I understanding that the right way? Yeah. So, and I want to pin your video so I can see you all. All right. So just thought I'd give you kind of a little bit of an overview, hopefully at the right level, for just how airplanes fly and how airplanes work. Does that sound interesting a little bit? Like, how many of you all, everybody's been on an airplane in this class, I assume, right? Because you have to get to school that way. Has everybody been on an airplane? Who thinks they know how airplanes fly, actually? A few hands? Not very many. Okay, good. So hopefully everybody's going to learn something today and find out something cool. I'll also say, if you all have, go online at all, find me on Twitter at Dr. Chris Combs. You can keep up with what I'm doing in the lab. See all kinds of neat stuff that I put on there about aero and space. Just a little quick thing about me. So I am in San Antonio, Texas. All right. This little star in the state of Texas, that's about where I am. This is where my office is, where my lab is. And so, we're a big research institution now, over 30,000 students, programs in mechanical and aerospace engineering, biomed, chemical, civil, computer, electrical, all kinds of engineering. All right. So look me up, send me a message when y'all start thinking about colleges and stuff, or even if you want to know anything about what engineering school is like here in a few years, send me an email, okay? And I'll talk about it. But really, what we're going to try and do here today in about 20 minutes is just kind of cover sort of the fundamentals of what makes an airplane fly, what keeps an airplane from flying, and like how they stay in the air, how they work it. And it really is amazing in a lot of respects, but hopefully coming out of this, you guys will have a little bit better understanding of what's going on with an airplane. And I think the big thing to know to start is if we have our airplane here, all right, we have our airplane, and you all can see these slides okay, right? And can you see my little laser pointer on here? Some thumbs up if you can. Okay, I'm going to power through anyway. So there's four main things that we've got to deal with that make an airplane fly or not fly. There's the weight of the airplane. There's this thing called lift. There's thrust, and that's moving the airplane forward. And then there's drag that's holding it back. And I'm going to take a minute and talk about each one of these. And then we're going to kind of put it all together and see if we can make any sense about it. So the first thing that's hopefully the easiest one to understand is just weight, okay? This is what's pulling a plane towards the ground, right, from Earth's gravity. And for even small airplanes, we're talking about thousands of pounds, right? Kind of the littlest airplanes are still over 2,000 pounds. The biggest ones that go over the ocean and things like that, carrying a bunch of passengers can be over 1 million pounds. All right. So there's a lot of weight that you're trying to get up in the air. And there's actually a few different pieces of this weight to keep in mind, right? We've got just the empty weight of the airplane itself, all right? Just all the metal and the components that hold this thing together. Then you've got the fuel, all right, because you got to carry the gas to make you go. So that fuel has weight that you have to account for. And then there's the payload, whether that's people or bags or cargo or whatever you're putting on the plane. All of these things weigh something. All of them contribute to how much weight you have to get off the ground. And so that's something that you can't forget when you're looking at these different forces on a plane, all right? So to understand a couple of these other concepts, something I want to point out is that air is a fluid, what we call a fluid. Just like you think about with water, all right? Air moves around in the same way. It actually follows the same rules, is governed by the same equations. There's things that we do in my lab and different techniques that we use where you can actually see this happening. And so, you know, this is like somebody's hand, and you can see the heat coming off their hand. This is a little drone blade, and you can see it slicing through the air, creating vortices, all right? And so airplanes are doing this too, and they're interacting with the air as they move through it. The air pulls on them, the air moves around when the airplane shows up. So that's something to remember when we're talking about some of this other stuff, right? So the next force, remember we have weight that's pulling us down, but what's pushing the airplane up? That's a thing called lift, okay? And so, hold on, let me just, there we go. All right, this thing called lift. And in these images here, we're looking at this kind of the side of the airplane wing at this shape that's called an airfoil. And it's this shape that helps an airplane have lift. And there's a couple different ways of kind of thinking about why this happened and why the airplane moving through the air with this airfoil shape pushes it up, okay? Because you shape the wing basically in a way so that the air over the top has to move faster to get around the wing. And when air moves fast, when it speeds up, it gets lighter. There's less pressure, all right? The air moving underneath the wing is slower, and so it's higher pressure. And so there's more force on the bottom of the wing pushing it up than there is on the top pushing it down, all right? And so that pushes up on the bottom of your wing and pushes you up into the air, hopefully more than your weight. That's what makes you fly, all right? Now, another way to think about it is, because of this, the way that this airfoil is shaped and the way that you angle it in the air, that air is coming in and you're pushing it down. You're pushing all that air down off the wing. And we know from Newton's laws about equal and opposite reactions, right? And so if you're pushing that air down, that's going to push the airfoil up, and that's creating a lift force. All right, so there's a lot of different ways to think about this and to visualize it. But that's kind of the fundamental force that's pushing an airplane up in the air. All right. Now, to generate that lift, you do have to be moving forward so that this wing interacts with the air that's moving into it. All right. You have to be moving forward to generate that lift. And we do that with this third force that's called thrust. There's a bunch of different ways to generate thrust. Really, the bottom line is thrust is whatever you're using to make you move forward. If you're throwing a paper airplane, the thrust is your arm, right? Throwing that airplane. But in a lot of planes you've maybe seen, a pretty common method for generating thrust is a propeller. All right. So that propeller is spinning. That's speeding up the air that moves through the propeller, pushing it forward, and that pushes your plane forward. And there's a bunch of different types of propellers, propeller designs, but this is a common thing we've been doing in airplanes for 100 years, right? So you've probably seen a propeller. So this is one of our ways that we generate thrust. Then another common approach you may be seeing is with a jet, all right, a jet engine. So, you know, a lot of different types of airplanes and commercial aircraft that are flying to different airports across the world and across the country are going to use a jet engine or a jet turbine or gas turbine. And really what this is doing, you've got something kind of like a compressor or kind of like a propeller that's called a turbine. And it's got these things called compressor blades on it, and they spin really, really fast. They suck that air in. They make it high pressure. All right. So you got this air coming in, you spin it up, get it high pressure, and then you mix that with fuel and you burn it. And then that turns into this hot, fast exhaust that shoots out the back of the engine that generates a lot of thrust. All right. And there's all kinds of different jet engines. You can have afterburners where you're lighting a little bit of extra fuel on the end and make you go extra fast. A lot of military aircraft use those. But this is another really common type of engine that you see on an airplane. All right, generating thrust. Now, a lot of people don't think about this one because you don't see it every day, but I like to remind folks, you can generate thrust with rockets too, okay? And that can still be an airplane. So this is mostly, you see this on experimental aircraft a lot. There's a pretty long history of using rockets to power aircraft. The X-15 that NASA flew at Mach 6 is one of my favorites, all right? But there's some really neat examples of airplanes that were powered by rockets as well, all right? So that's, one you don't see every day, but still, you got to move fast somehow, right? You can, sometimes a rocket's the best way to do that. All right, our fourth force to talk about. And I still can't see you all, so hopefully everybody's getting this, or you can drop something in the chat if you're, if you need me to back up or slow down or visit something again, okay? The fourth force is drag. And in some respects, you might even think about this as the opposite of lift, but it really is, it's the air pushing back against the airplane. That's probably the best way to think about it, because like I said, the air is a fluid, and you can actually, that air is going to interact with the plane and pull it back and push against it when the airplane is trying to go forward. And so this decreases how much lift you get, how much and how fast you're going. All right. As kind of an illustration of why airfoils are shaped the way that they are and why we use this shape for a wing, why aircraft are shaped the way that we are. If you just had a flat plate, if your wing was just like this, all right, like your hand, it kind of, the air moves around it in a funny, not friendly way. That's not very efficient. If you turn that into a cylinder, all right, like a pipe, that's about twice as good as just that flat plate. You get 50% of the drag as you do from a flat plate. But then if you do what's called streamline that, all right, so you make it this nice kind of teardrop shape, then suddenly you've only got 10% of the drag, all right, 1/10 of the drag you would get from just a flat plate with this streamlined shape. And so that's why wings are shaped that way, because they're going to be much more efficient. They use less fuel, generate more lift, which is what we want. We want to be able to fly high. And this is an example of, like, you can actually see when you do, this is from a simulation done on a computer. You can see how the air interacts with these wings. It pulls back on the aircraft. This was actually an experiment somebody did where they lit up some fog, and you can see what interaction the airplane has with that fog as it rolls through it. The vortices on the wingtips spin that around. All right. So drag force is always something that we're fighting against when we're flying, but if you have enough thrust and enough lift, you can overcome that. All right. So to kind of revisit these four forces and talk about what exactly they mean. All right. If our lift is more than our weight, then our plane goes up. Right. If we have more weight than lift, basically, if we're not producing enough lift, then the plane starts to go down. All right. Similarly, if you have more thrust than drag, you start going faster. All right. You're accelerating, which a lot of times is going to also produce more lift. But then if your drag is greater than your thrust, then your plane slows down. And so this is how we control how fast the plane is going, how high it is, all right? And so sometimes you can use these things to your advantage. If you're trying to slow down, then you want to create more drag or decrease your thrust. If you want to come down to land, all right, then you want to decrease the amount of lift that you're producing. So these are all things that pilots consider and that are integrated into controls of airplanes as well, so that we can move them the way that we want to move them. And there's all these different pieces to an airplane and parts that make the plane do the things that we want it to do. All right. So we have our engine. And so maybe that's a jet. A lot of times the jet engine is going to be located under the wing here. For a propeller aircraft, they might be located up here at the front, or, sometimes they're on the wing. We have all these different things called control surfaces. All right. These different stabilizers and rudders and elevators and flaps and spoilers and slats. And all these things are there to, one, control how much lift and how much drag we're making in case we want to go up or go down or speed up or slow down. But then there's also these 3 different control directions for an airplane. All right. Because it's not just like going, walking or driving a car where you just go side to side. An airplane is free to move in all 3 axes. So if you're looking at an airplane head on, we have the roll axis. All right. So it can go like this. And the wings go up and down. And you control the roll with these ailerons, all right, that are located here on the wings. And they go up and down like that so that you roll. You have yaw, okay, and that really is the moving side to side, right? That's yaw. And you do that mostly with rudder, okay, with this fin right here. And then you have pitch, and that's pointing up and down. That's pitch. And you can do that with the help of some of your flaps, all right, and with your elevator on the tail here. And that's going to move up and down, and that's going to help you move up and down. And then this is kind of what that looks like on a real airplane, maybe an airplane similar to one that you've seen, all right? And you've got all these different surfaces. They try to blend them into the body so they're nice and smooth, but you see all these different pieces, and you can even see the shape of the airfoil that we talked about, right? And there's a bunch of different airfoil designs, a bunch of different types, but for most aircraft, they have a shape similar to this one when you look at them from the side, and that is so that air goes slow on the bottom and then fast on the top. And again, we do that because the faster air, it's going to have lower pressure. The slower air is high pressure, and so it pushes up on that wing, and that's going to push you up into the air. Now, another thing I wanted to talk about that people think about in designing airplanes and in flying airplanes is this concept of stability, so that you don't get out of control, basically. So that you're always in control of your airplane, and then if it bumps around, it always settles back in where you want it to be. There's a few different types of stability, and you can think about this with like a styrofoam cup or a plastic cup. Imagine if you put a cup, just set it on a table upside down, all right, like this. If you push on it one way or another, tip it just a little bit, it's going to fall right back to where you had it. And that's called positive stability. And that's something that we want in a system. It's also the same as like a ball that's on a piece of paper that's like this, all right? If you roll it one way or another, it's always going to go back to where it started. That's what we want our airplane to do. You also have this thing called neutral or static stability, all right? And this is like a ball on a flat thing. You roll it, it's going to go in one direction, but it's not going to speed up or do anything crazy, okay? We can sometimes live with that, but we don't really prefer it. But what's really bad is negative stability, all right? And that's like if you have a cup that's upright, if you tip it, it's going to tip over, all right? Or a ball, imagine a ball on the top of the hill. You push the ball a little bit one way and it's going to roll all the way off the hill and it's not going to stop. We don't want our airplane to be that way. We want our airplane to be like this, where if it moves a little bit one way or another where it's not supposed to, maybe from some turbulence, it's going to settle back into where it's supposed to be. And the way that you do this is you think about and account for these things called the center of pressure or the center of gravity or the center of lift. And this is kind of like where the weight and these forces are concentrated and where they act from. All right. So with an airplane, what you do is usually have the center of gravity forward on the airplane in front of the wings. So you have this center of lift kind of close to where on the center of your wing. And then you also have this second force from the tail. All right. And what that does is it makes sure that if you get pointed nose down, the tail pushes you back to balance you. All right. And then if you get pointed nose up, that force pushes on the tail and you rotate about the center of pressure, the center of gravity, and that pushes you back to level. All right. So that as you're flying, if you get one way or another and you didn't want to be, that tail is going to help you stabilize and get right back to where you were supposed to be and flying flat. All right. So that we're never out of control, and that if you end up pitching one way or another, suddenly that doesn't get to be a runaway thing and you lose control of your airplane. Now, an important thing to remember, though, that's tricky about airplane design is this is true in all of our axes of motion. All right. So you actually have to have stability in roll, in your yaw, and in that pitch axis. And so that's a tricky thing for aircraft designers to make sure that they handle all of those requirements so that if you move any one direction, you're not going to go unstable and fall off a cliff, basically. Now, the last thing I wanted to talk about was just a quick overview of just how many different types of airplanes there are. I don't know how many of these you've seen or how many of these you've heard of, but whether it's a commercial aircraft or like a light aircraft or monoplane type thing. But hey, we've got these military jets that are in a totally different flight regime, and they look different for a reason, right? All of these things look the way that they do for a good reason, right? The engineers designed them that way. You've got kind of an old school biplane. Those are still out there. What about seaplanes? Do you all see those up there? Sometimes, yeah, maybe. There's people that fly gliders that actually don't have any thrust. They get up in the air and then they float around and ride on thermals in the atmosphere. UAVs and drones are getting really popular. There's private jets. You've got these big, massive cargo aircraft that we work on down here in San Antonio sometimes. There's a really fun one. This is a V-22 Osprey. It's called a tilt rotor airplane. It can actually act like a helicopter or an airplane. And so it's got these big rotors that act like propellers, and they can rotate so that they're up or front, and it folds up like a transformer. One of the coolest airplanes you'll ever see. And then there's this whole class of experimental airplanes, all right? They look all kinds of funky shapes and sizes and do lots of weird things, and sometimes they've got rockets on them. So there's this entire world of airplanes that have different function, different form, and are there for a different purpose, you know, depending on what people need them for. So that is my, 15 minutes on what is an airplane. And something I always like to ask people, are space planes an airplane? Is a space shuttle an airplane? Is Spaceship One an airplane? What do we think? Raise your hand if you think that's an airplane. A few of them. I kind of like to think that it is, but it's very much open for debate. You all can argue with your friends and parents about that one, all right? See what they think. But with that, I wanted to kind of get us back on time and open it up if there are questions. We talked, if you all want to go back to the other room, we can do questions, or if somebody dials in, you can use the phone, or you can just type them in the chat. Whatever's easiest for you. And I'll stay here and answer anything that you want to talk about, because I tried to keep this at a level that I hope everybody was able to stick with it, but I'm sure for some of you, this wasn't as deep as you wanted it to go. So any kind of questions or things you want to clarify or talk about more, I'm happy to do that while I can.
Dr. Combs, I did see one in the chat box already.
Great. Let me pull that up so I can see it. Okay, awesome. Okay. So do drones have the same movements? Yeah, so drones are governed by the same 4 forces, all right? But they are generating their lift with these rotor blades like this, right? And so they're pushing that air down and that pushes them up, but they still have weight, they still have drag, and that thrust is going to be generated depending on which direction they have those rotors turned. So they still do have all the same 4 forces that they're dealing with, just sometimes pointed a different direction. It's a great question. Yeah, Wayne, so I did have a couple slides on the backup on that. I could talk very quickly about what I do if you want to. Yeah, so the blue one, okay, the blue thing right here. This is a balloon, all right, that we popped with a laser, and we imaged it with a high-speed camera. So that's the type of fun stuff that we do in our lab. This is popcorn popping, imaged at very high speed. All right. You can see the kernel open up. That's kind of a neat one. This one, this is a COVID thing, mask versus no mask. You see how what somebody's breath looks like. This is a drone thing. This is a drone thing. And this is a device called a fluidic oscillator that actually, it gives you a jet that sweeps side to side, but there's no moving parts on the inside. So it's kind of a neat little magic trick. So I can keep talking airplanes and stuff, and if you all have questions, or I can talk hypersonics for a minute too, if you want to know a little bit more about what I do specifically.
Yeah, Miss Minot, if you guys want to type stuff in the chat, feel free and we can see the questions there.
Yeah. Will the plane get damaged each time it lands? If you designed it well, it better not, right? You know, we like to joke, any landing you can walk away from is a good landing. And if the plane still flies, it's a great landing, you know? But airplanes, if you look, let's look back at this. So even the space shuttle, all right, has these tires on the bottom of it. And most of these airplanes, you can see they have these tires. It's called landing gear, all right? And sometimes it's out all the time. Some, with certain aircraft, it goes and retracts inside the body and then it comes back out. And those wheels are there so that you come down on the runway and you land, all right? And those wheels absorb that contact and keep your plane safe so that it's good to take off again. So if you land your plane the right way, and if it's a well-designed aircraft, it hopefully doesn't get damaged when it lands. All right, I'm gonna start talking about, oh, okay, what is that experiment airplane? That is the Air Force NASA X-24B, which was a very cool project. NASA had this entire class of experimental aircraft as part of this thing they called their lifting body program. That sort of led to some of the stuff that we needed to know to build the space shuttle. But at the time, this flat bottom was a very, very new design that we didn't know how that was going to work. And they were testing out how some new aircraft shapes were going to work. And there's this whole series of these, but the X-24B was a pretty cool one. Okay, so why do cylinder shapes generate more lift than flat shapes? A couple of things to kind of clear up. So when the aircraft body, that's a cylinder, all right, but pointed in a different direction. And it's not really shaped that way to generate lift. It's shaped that way to reduce drag. So we're shaping an airplane like a cylinder in this tube so that it doesn't generate as much drag. It's more streamlined, okay? Now, why are airfoils shaped the way that they are? it really is about, okay, you see how with this flat rectangle shape and this sphere, when the air moves around, it gets back behind here and kind of makes some circles and spins around. That's called a wake. It's the air actually doesn't stay attached to the body all the way around. That's called separated flow. All of that creates a lot of drag, basically. All right. Because another way to think about drag is you want to have higher pressure back here because it's pushing you forward. When you have low pressure back here or suction, it's actually pulling you backwards, which you don't want. So one nice thing about these shapes when they're streamlined is they keep that flow going nice and smooth and attached and everything moving around it the right way. So you don't get separated flow behind that generates a lot of drag. But also these airfoils are shaped this way so that the air moves fast over the top and then it slows down and almost gets kind of stuck on the bottom so that you get a big pressure difference across your airfoil surface. So you get high pressure on the bottom that pushes up and low pressure on the top that also kind of pulls you up. So hopefully that answered your question. But that's a complicated concept. All right, I'm going to keep rolling, but if I see other questions pop up, I'll stop and circle back to them. So I'll keep an eye on the chat. But just want to give you a 2-minute overview because I think you might think it's cool of the type of work that I do. And this is called hypersonics. All right. And when I'm talking about hypersonics, I'm talking about things that are moving really, really, really fast. So 5 times faster than the speed of sound, like 4,000 miles per hour. All right. This is like a commercial jet or an airplane is usually moving about Mach 0.7, which is 0.7 times the speed of sound. All right. And any kind of airplane, like a smaller aircraft, is probably maybe even moving half that speed at most. Fighter jets are like Mach 2. A bullet also moves about Mach 2. I'm talking about Mach 5 and up. And we actually built a Mach 7 wind tunnel here at UTSA where we do research, all right, on hypersonics. The reason we care is because defense applications, everything in space is going that fast, all right? And there's also people out there working on airplanes that go that fast that can get you around the world in an hour, right? But these are speeds faster than 1 mile per second. When you start moving that fast, you get really, really hot on your vehicle surface to the point where it's hard to design things that can handle the heat. And you pounding into the air so hard with your vehicle that you break apart the air molecules and the chemistry gets all weird. And then also there's the problem of how do you even make something go that fast? And so propulsion is something that's really challenging. All right. So it's a fun problem. This is just an example from San Antonio. A commercial aircraft in 15 minutes covers this circle. At Mach 7 in 15 minutes, you cover almost the entire continental United States. In 30 minutes, we can get to Maine and past Seattle. We'd be able to fly from San Antonio to Alaska in like 45 minutes at Mach 7. So you're talking incredible speeds. You all, if you had a hypersonic airplane in Alaska, you could fly to Los Angeles and have dinner and be home in time for bed. All right. It's teleportation type speeds. And so there's people that are working on that. That's really cool. And we're doing research here at UTSA in this wind tunnel that we built that's been running for about a year. We do some really neat research. If any of you ever come down to Texas, I hope you can come and visit me and check it out. I would love to show you around. All right. This is what it actually looks like in person. We've got about 20 students that work in this lab and doing research in my group. All right. And like we do stuff for NASA, Air Force, Navy, DARPA, a bunch of other 4-letter organizations you haven't heard of. And so some really neat things that we have going on. And yeah, this is more fun videos. We also do things that blow up because we do propulsion work. So we light things on fire, make explosions. There's a lot of neat neat stuff that we work on. I want a hypersonic plane too, trust me. Yeah, that's what we're working on. We're trying to make that happen for you. And we have a lot of fun with our high-speed cameras. We do a lot of, because we're looking at hypersonics and everything moves so fast, a lot of the stuff we do is with cameras that are very, very high speed, that are 100 times faster to 1,000 times faster than like slow-mo on like a cell phone. So we can image these things happening really, really fast. How did I get interested in researching this? I mean, to be honest, I was a Star Trek kid growing up. Okay, so I was watching all, and you know, I like Star Wars too. All the sci-fi, give it to me. And so I wanted to build spaceships. I wanted to build rockets and airplanes. I've always been fascinated by this kind of stuff since I was your age, right? And so I got into aerospace engineering in school. Went to college to study engineering. And then I ended up in a research group that was doing hypersonics as a graduate student when I was working on my PhD, and I've been doing it ever since. But yeah, I was inspired by the space program and by science fiction. Just always thought that stuff was neat, and I've kind of been doing it my whole life, honestly. If you've got other questions, just put them in the chat. I think we do have a couple more minutes. And if there's anything you all want to know about airplanes that I didn't touch on, feel free to jump in, right? If you've got burning questions, even if they're a little more detailed, I'll give it my best shot. I personally cannot take kids to space, but I think in these kids' lifetimes that will happen. We've already seen Blue Origin developing basically a space tourism type thing where people are getting launched up in a capsule up into near space. All right. So we're working on it. Yeah, I think that that's going to be happening pretty soon. It's expensive right now. That's the only thing. I think the tickets are like $100,000. So I'm hoping they can drive that down. Who would like to go to space? Some of you, I'm not sure if I want to go to space or not. I'm still trying to decide. It makes me a little nervous. I like watching better. Oh, great. That's good. Well, I hope they get a chance. All right. Any other questions from Alaska while we're here? All right. I do hope that you all learned something. I hope this was a little bit interesting, at least a bit of a break from your normal routine. Thank you all for sitting and listening. Oh, we got another question. Any special features that planes need to adapt to cold weather? Yes, a couple of things to think about. One, when you go up way high in the air, it's actually really cold up there. And so most planes are designed to be able to handle cold temperatures. Like the difference in the upper atmosphere is not as extreme. So pretty much all planes, regardless of where they take off from, they're pretty cold pretty fast. But in terms of taking off on the ground, one thing that is a big deal is ice, because having ice on your wings can be really bad. If your engines are too cold and they aren't able to start, that's a problem. So you see a lot of work done on de-icing and making sure that you've got snow and ice off of the airplanes when they take off. And you also want to prepare the runway the right way so that just like if you're driving on a road and there's snow and ice on the road, that's dangerous. It's dangerous for an airplane to try and take off and land on a runway covered in snow and ice. So it's about prepping the surface and also making sure that the wings especially don't have snow and ice on them. Okay, yeah, I would love to have y'all down to San Antonio. So if you all can make it down, I'll be here. Consider it an open invite. And I will say in the meantime, before you come down to San Antonio, everybody feel free, check out my online profile. We've also got a website. If you just search my name on Google, a lot of this stuff will just come up, all right? Because I've got a pretty easy to access web presence. And if you all have stuff that comes up, feel free to send me an email with follow-up questions too. And if you can't find my info, I know Wayne's got it too.
Well, guys, I just want to thank everybody here. First of all, I want to thank the students for your participation today.
Absolutely.
Thank you so much for being great learners and a great audience today. We want to thank you, Principal Minot. Thank you so much for helping get this orchestrated. We want to thank UTSA, all you guys there, Miss Ford, Mr. Velez, Dr. Combs. Y'all have been amazing today. And of course, Mr. Fagan, thank you for having this idea and putting all this forward. This is fantastic. It's been a wonderful experience the last hour.
Okay, and I saw another question come in. I just want to handle this. How to deal with ice fog on airplanes? So there's a couple of things to keep in mind. One, like I said, they treat the wings for ice. And so there's chemicals that you can spray on the airplane that are de-icers that help get rid of the ice. All right. And you can clean the ice off the plane before it takes off. But then the fact of the matter is there are certain types of weather conditions where it is just not safe to fly. You don't want to fly through a storm. You don't want to fly into a bunch of ice and snow. So sometimes flying is just not really possible. But you do everything you can with the plane to make sure that it's in good condition when it takes off, and you've got some chemicals on the wings to keep them from getting frozen. All right, well, thank you all again for paying attention and hanging around. This has been a lot of fun for me too.
Guys, we're a great audience.
Wow, you fly at -40. That's wild. That's impressive.
Well, you guys have a wonderful day, unless y'all have on the last minute things. It was great to see you guys.
All right, thank you. Birds up. All right, take care, everybody.
Bye.